In this video, we're going to introduce some really important concepts associated with these linear transformations. And before we get into these concepts, I'm going to give a name to a special type of transformation. Now, the name itself isn't particularly important, but it's what the transformation does. So let's start. So if T is a transformation, I'm just going to keep it a bit general here. Let's say we go from Rn to Rn. And what I'm highlighting here is that the domain is equal to the codomain, right? So if you have a transformation that takes vectors, let's say in n space, and then transforms them and produces other vectors in n space, this sort of transformation is called a linear operator, right? So if T maps from Rn to Rn, so T is called a linear operator. All right, so in this video and in the next few videos, we're going to focus on these linear operators. Now, what do we know about them? Well, we know going from Rn to Rn, there's always a matrix like at the heart of everything, right? So in this case, because the dimension of the domain and codomain are the same, then our matrix would have to be a square matrix. It would have to be n by n. So I'm just going to denote our transformation like this. As usual, it's A times B, and now the dimension of A, right, is n by n. Okay, so what we're going to do is I'm going to give an example of one of these linear operators now, call them linear operators. And I'm just going to keep it fairly simple so that we don't get too bogged down in the computations or anything. But let's go from R2 to R2. So let's say we're just looking at vectors in the plane. And then here is the actual transformation. So I'm going to use a matrix that on the surface, well, and then not even on the surface, but in any regard, it's not really, there's nothing special about this particular matrix, right? So there's our 2 by 2 matrix, and then that's going to multiply our vectors. So I'm just going to pick a couple vectors and apply this linear operator and see what happens, right? Let's just see what happens. So let's say v1 is the vector. I'm going to keep this pretty simple, just 1, 1, right? And again, we could sketch these if we want, but I think I'm not going to focus too much on the geometry right now because I'm just trying to introduce these concepts. So let's take the vector v1, which is 1, 1. That's our pre-image, and then let's see what the image is under this particular linear operator. So we're going to take our matrix 3, 1, negative 4, 8. And then we're going to multiply that column 1, 1 and see what happens. So let's do our matrix multiplication. So if we do our first row along with that single column, we'll have 3 times 1 plus 1 times 1. So that's 3 plus 1. And then if we do our second row, again with that column, we'll have a negative 4 plus 8. And then if we simplify this, we get 4 and 4. Okay, that's kind of interesting. You know, so we start with the vector 1, 1, and then when we operate on it using this operator, we get the vector 4, 4. Now, what's interesting is when we look at our pre-image and compare it to the image, we see that there's actually a simpler relationship between the two. In fact, notice that I can actually factor out a 4 out of this, and I can express this single vector in terms of scalar multiplication. So I can say it's 4 times the vector 1, 1. And that's kind of interesting because we started with the vector 1, 1, and then we applied this operator, and then we ended up with a vector that's 4 times what we started with, right? And I'll just highlight a couple other things. So here we did our matrix multiplication, right? So we did our matrix multiplication there. That's what our operator does. But then it's the same as, looks like just scalar multiplication. Interesting. And then it begs the question, does this work for other types of vectors? You know, like I did the vector 1, 1. Does it work for other types of vectors? Well, the way we can test this out is, again, just sort of pick another vector. So let's just change one of these components. Let me just make this, let's look at v2 and look at the vector 1, negative 1, and again do our transformation. So sorry, I should put a 1 right here. Right? So now let's transform v2, and then we will have our same matrix as our standard matrix, 3, 1, negative 4, 8. And now let's multiply the column 1, negative 1. All right, so again, we're going to do a matrix multiplication. But now, because there's a negative 1 here, I'm going to have 3 minus 1. And then I'm going to have negative 4 minus 8. So negative 4 minus 8. And then we simplify. We have 2 and then negative 12. And it should be pretty clear now that 2, negative 12 is not a scalar multiple of 1, negative 1. So I'm going to say this is not a scalar multiple of 1, negative 1. So no matter what k I want, and here are our set of scalars is real numbers, there's no constant that I can find to satisfy this relationship, right? So right away we see that this kind of special relationship that we saw with V1, it is in fact very special because it obviously depends on the vector. All right. So this idea of certain special vectors that when they are transformed just ends up being scalar multiples of themselves. That's the concept that now we're going to explore in this video and several other videos related to, and we use certain terms to describe these special kinds of matrices. So let's actually give the definition now of what an eigenvector is and what an eigenvalue is, right? So the fact that you hear vector, and I'm pointing out that these are special vectors, you probably think that my little example here has something to do with what we're about to define, and you would be correct. All right. So let's say it this way. So if when we transform a vector, we simply get, and for historical reasons, the symbol that we tend to use for the scalar, the constant right here, we're going to use lambda. So if t of v is equal to lambda times v, and then let me put some restrictions on these. For one, we don't want our eigenvector to be the 0 vector, right? So if you think about it, if I do my matrix multiplication with the column of zeros, I will always get a column of zeros. So then I could have pretty much any constant I have here that would satisfy that equation. So essentially we want something that's non-trivial, right? We want an actual vector, and let me just appeal to geometry just for a second. We want to have a vector that has both magnitude and direction, right? So we don't want our vector to be the 0 vector, and then but our lambda can be any scalar we want, right? So if you have an operator like this that takes a vector in one space and then returns a scalar multiple of the vector in the same space, and this is what we say. So we say V is an eigenvector of T, and we could also say of A, because we know the matrix is the heart of all of this. So I'll just say it's an eigenvector, right? Eigenvector of T, and I'll put in parentheses of A here, right? With eigenvalue lambda. So with eigenvalue lambda, right? So the vector is referring to the special vector that will get scaled whenever we apply this operator to it. And the scalar that does the scaling is called the eigenvalue. And they kind of go in hand in hand, right? They're it's a special vector, a special constant here, and then we refer to both of them sometimes as an eigenpair. So we refer to lambda comma v, and I'll put them in parentheses, right, as an eigenpair, right, eigenpair of t, right, and also of a, right, same thing, one and the same, right. And that's really what we want to accomplish here, is to give us the definition of this, right? And the idea is that the eigenvector is a special vector that when we transform it, it gets modified just by scalar multiplication, right? Now, as far as the scalar multiplication is concerned, it could be any scalar, right? Remember, I didn't put any restrictions on what the scalar is. So let me just highlight a couple things and then just give you some more terminology and then wrap this introductory video up. So when your lambda is greater than 1, it stretches the vector in the same direction. So what I will do here is just kind of visually now. So when your lambda is equal to 1, let's say this is our eigenvector, right? What it would do is it would stretch it. So I'm just going to do I'm going to do the image in a different color but dotted. So it would just make it longer. So then this would be t of v, right? If our scalar is between 0 and 1, right? So we're basically just looking at all the possibilities of our scalars, right? So if our scalar is between 0 and 1, let's say this is our v, this is for eigenvector, then the image of this eigenvector is going to be a vector, again, in the same direction, but shorter in terms of the geometry. It will be maybe just that vector right there. That will be t of v. Doesn't really seem interesting, but it actually is. If lambda is equal to 0, what happens is it kind of annihilates the eigenvectors. It just kind of wipes it out. So if, for instance, this is our v, then the image of v, again, think about it, if I multiply this vector by 0 as a scalar, then I'll get the 0 vector, which we tend to often just represent with a point, right? So yeah, it just kind of annihilates it. And then if lambda is between -1 and 0, so if it's like this, if our lambda is like that, then what will happen is, if this is our vector, now the fact that our scalar is negative, oh, sorry, this should be a 0, right? The fact that our scalar is negative, it's going to change the direction of this, not just any old change, but a 180, so it's going to flip the direction, but it's also going to shorten the pre-image, right? The output, I'm sorry, the output. So this will be basically our t of v. And then if our lambda, last case here, if our lambda is less than -1, then what will happen is it will make it longer, but in the completely opposite direction. So if this is our v, keep writing our v here, then the image of this now will be all the way down here longer, so that will be like t of v, right? So yeah, we basically just visually described all the possibilities as far as the eigenvalue and the eigenvector is concerned, right? Just again, a couple other terminologies. The word, or I should say, the root eigen actually comes from the German language, and it has lots of different ways that you can sort of translate it. You could say own or proper, but it can also be used to represent something like characteristic, right? So it talks about you know the almost like the character of the linear operator, in that what does it do to these special vectors, right? And the word characteristic is going to come up in subsequent videos when we go a little bit deeper in this uh, topic. And then the spectrum, so let's fix that. The spectrum of our transformation or operator, so the spectrum of T and also of A is simply the set of all eigenvalues, right? So is the set of all eigenvalues. So once we figure out how to find these, if we find all of them, we call it the spectrum of our operator or of the matrix. And it's often denoted just lambda, because again, we're using lambda, and then we put the matrix A in parentheses. All right. And then this idea of the spectrum, and it leads to something bigger that's called a spectral analysis, which I'm not going to write down, but that's a huge thing when you're dealing with the issue of finding eigenvalues and eigenvectors. All right. So that's the idea behind an eigenvalue and an eigenvector. And in the subsequent set of videos, we're going to focus on how to compute these things. So suppose we only have the matrix. How on earth are we going to find two unknowns, right? The lambda and the v, right, or scalar and a vector, if we just have one operator? Like how can we do that? Well, that's the power and the beauty of algebra, which we will explore in the next video. So see you then.